I've really enjoyed the conference, so thanks to Boris and the other organizers. This has been super fun, and I've enjoyed it. I'm going to try to connect to some of the existing talks, like Elvis's talk on scaling laws and Dan's this morning, as well as I know Boris's talk at the beginning discussed some of these scaling limits of neural networks. So I basically want to think about two things. One is, what kind of limits do you approach if you make the neural network infinitely parameter? Like you take a parameter limit where the number of parameters diverges either by taking depth or width to infinity. What kind of training dynamics do you get in that limit if you randomly initialize all of the weights? And then the second question is sort of how fast do you approach the limit? So what is the sort of rate at which you converge? And that's going to be our proxy for modeling neural scaling laws. So we're in this era of like scaling up large language models or transformer models and like vision problems and language modeling problems. People take people make plots where they plot compute on the x-axis, either increasing the number of training steps of the model or the size of the model, or both simultaneously. And there's usually a very sort of lawful behavior, very regular behavior over many decades of the scaling performance, and it usually follows a power law. So this is from the GPT-4 technical report. And they claim that we trained all these models, and then we were able to kind of extrapolate the performance, and we trained the really big model at the largest possible size that they could afford to do it for that run. And then, when I stare at this, I wonder, is there something that would happen if you took the parameters count to infinity? Could you characterize the kind of limiting dynamics you'd encounter there? And what sets the scaling law? So what sets the rate at which you approach this limit? So often people observe these things scale as model size to the minus alpha, where alpha is some small number like 0.3. Where does that come from? Do we have any solvable models where we can understand that? And so in this talk, I'm going to first try to think about limits. So I'm going to first think about infinite width and infinite depth limits of neural networks. And then we're going to try to come up with a kind of toy model that captures some of these neural scaling laws in terms of simple spectral properties of the data distribution. Okay, so
in this plot, you're equating the size of the model with the amount of compute.
So it's not always the case. Sometimes people are scaling them both jointly. Like compute could be like number of training horizon, so like number of tokens observed during training, times the model size, times parameters. So it's like total flops is usually plotted. But you could also make a curve that's just at a fixed training time, I vary the model size, and there's a regular improvement until I hit some limit that's set.
So what's a scaled model? When you scale the size with the amount of compute, or they're the same model?
So this particular plot, this is the GPT-4 paper. They didn't give a lot of detail. So it's unclear if this is a fixed number of steps and they're varying the model size, or if it's changing the model size, keeping the model size fixed and varying the number of steps. But the whole point is just there's an extrapolated thing. And in general, there's usually there's like chinchilla-like scaling laws where you have the loss as a function of time or like tokens and model size. And then you could plug in like a compute budget and figure out what this curve should be. We'll have a solvable model of this in a second. Did that answer the question, or?
No, that's
I don't actually know. Like,
confused.
I don't know what is actually being varied in this plot. I should probably just use the chinchilla plot or something. Okay. Okay. So yeah. So first, let's just think about width. So here's just a simple MLP. So with every hidden layer has n neurons. And let's say I have L layers. And the recurrence is basically I take my data, I pass it through the first layer weights. That gives me the pre-activations, which I'm going to call H for every neuron in this layer. So I'm going to call H the pre-activations. And then there's a recursion. So if I know H in layer L, I can get H in layer L plus 1 by going through a element-wise nonlinearity and then summing against weights. I'm going to use a 1 over square root of n factor here. And this just ensures that my signal propagation is reasonable at initialization. So this is a sum of n random variables, and like all the w's are mean 0 at init. So this gives me a sensible variance for the scales of these h's. And I'm going to do everything like that, except in the last layer, I'm going to allow myself a potential scale factor gamma that can control what parameterization I'm in. So the game is I want to figure out what happens if I just took random weights in every layer and then did some gradient-based learning on top. So that's the game. We want to figure that out. So it's known from previous works that if I just multiply my output by some scale factor, it can kind of control the relative rate at which the outputs of the model move compared to the internal the internal representations of the model. So in the limit where this gamma is just a fixed number, and I scale up the width in of every hidden layer, this is known as neural tangent parameterization. And in the limit of infinite number of hidden neurons in this limit, you'll actually get what's called a kernel method. So in this limit, all the h's throughout training will actually be frozen random variables. But the function f will move. So you'll learn a function, but you'll learn a function with kind of random features that weren't updated in a task-specific way. There's this alternative scaling that, depending on the paper you read or the setting, it's known either as the mean field or the mu-p kind of parameterization, where in the last layer, you basically need to do something different. You need to choose this parameter to scale with square root of n times a constant. If you do this and take width to infinity, then all of a sudden, the pre-activations in every hidden layer move at the same rate as the function. So these are two different types of scaling limits for large width. So what's actually at stake? So what's a better model, let's say? Let's say I take an out-of-the-box, just like standard CNN. I train it on a couple of passes over CFAR. I start with, let's say, a 64-channel model. So this is my initial width model. And there's two ways of extrapolating from this finite model. I could first extrapolate in this NTK parameterization, right, where this is the 1 over square root of n in the last layer. So if I do this, right, I spend more and more compute. I get a larger and larger model, but the training's actually slower. So why is this happening? This is happening because the kernel's actually at width 64 is learning features. The features are being updated. As I go to width infinity, I'm eventually going to get the loss curve for a kernel method. So the training's going to be slower. OK, so if I instead increase the width in this mean field scaling, or this mu-p scaling, then all of a sudden the dynamics are much more consistent. And if anything, as I increase the width, I get better performance. So I would argue, like, if we wanted to model or like a certain type of scaling limit for infinite width that captured the same kind of behavior or better than the finite models we encounter in practice, I think we should try to make models of this mean field limit instead of the models of the NTK limit. Yeah, and basically I think that these models are generally closer in terms of the kinds of representations they end up having after training and their loss dynamics. So the game is we want to model this. OK, so what we're going to do is, the whole story is basically what happens at infinite width. So now we have this kind of feature learning thing. Is there any way you can describe it? What kind of statistical properties does it have if I randomly initialize all the weights and then train with gradient descent? So basically what we can do is we can provide this dynamical mean field theory that tells you how what the function is computing, what the internal representations of the network look like. And this is an idea from the physics of spin glasses, where you have disordered energy functions. You have a bunch of spins or sites, and they all interact with kind of random interactions. But then at the infinite system size limit, they're described by a random single variable that interacts with some bulk statistical process. So in our case, what is this going to mean? It's going to mean at finite n, we have some complicated interacting neurons that are hard to characterize. But as I take width to infinity, the neurons kind of become independent. And they're only coupled to deterministic population averages. So the interactions are sort of mean field. They only interact through, you could say, like as Boris would say, the empirical measure of the activity of the neurons. And so the scaling laws are, so this is going to be what we're going to talk about in the limit. And then for scaling laws, we're going to have a simple kind of analysis of through training. I think about a training horizon, and I think about varying model size. And what we're going to try to do is come up with a model of compute optimal scaling laws that depend on something about the task and something about the model structure. Yeah, and the three resources we're going to vary are training time, model size, and total available data. So those are the two things we want to try to do in this talk. OK, so let's, everything I'm going to say applies to discrete time, SGD or GD, but let's just, for the sake of simplicity, think about gradient flow. So let's just say I have a loss function. There's some data distribution P of x. I have some loss function at each point F of x. This could be P of x, this data distribution could be just a discrete set of points and P training points. Or if I'm doing small learning rate online learning, this could be my test distribution, my population distribution. And so the gradient flow dynamics are just going to look like, I take a derivative of whatever this loss function is with respect to the weights, and I update it. So it's well known that there's this reparameterization where you can, instead of thinking about weight dynamics, you can think about how is the predictor, or my output of my model f on each data point x at time t, how is this evolving during gradient flow? You can express it in terms of a time-varying object known as the neural tangent kernel. And this delta is just some derivative of whatever loss function I have with respect to the output. And this NTK object is it's an inner product over basically parameter gradients for every layer. So if I knew how this K object was evolving through time, I could integrate this equation and I could figure out what kind of predictions my model is going to make. So that's the game. So we want to find a way of figuring out how to calculate this K through training time. So this kernel, right, it's this inner product of parameter gradients. It breaks up into contributions from every hidden layer. There's two components. There's basically a component from the feature kernel, which we'll call phi, and the G, which is a gradient kernel. So the gradient signals are like the back-propagated signals. So if I imagine a neural network, there's a forward pass and a backward pass. So Gs are what I would basically be computing if I did a derivative of my output with respect to a hidden activation in some hidden layer. So you would compute that with backpropagation. And so these feature kernels are basically going to be time-dependent. So this is basically like I look at the representation in hidden layer L, and at pairs of time points TS and pairs of data points XX prime. So if I knew these objects, phi and G, then I can get K, and if I know K, I can get F. So that's sort of the game. And okay, and what we're going to find is this parameter gamma 0, right, which is this feature learning kind of parameter. This is a knob that'll persist even in this infinite limit. And if I take this parameter to 0, now this is an order 1 scalar that kind of, as I take this to 0, I can get a kernel limit still, but I don't have to. I could also maintain feature learning. Okay, so we don't want to be in the gamma 0 equals 0 limit. We want to actually figure out what's happening in the rich regime. Yes? Yeah.
So maybe I'm just trying to get my head around your notation, but capital phi L, there's a T and S there, but where are they? Where is there implicit like integration happening somewhere? Because I don't see them above. I don't see T and S above.
Oh, okay. There should be like this is evaluated at time t. So this could be t comma t, t comma t. Right. But in a second, we'll actually have to track, unfortunately, pairs of time points because there will be correlations across time that are important. That's a good question, though. Any other questions? Yeah. 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 So I think I might have flashed through it, but gamma 0 is going to be the effective order 1 version of feature learning. So yeah. So the raw value that we had in this denominator, I'm saying it's an order 1 knob gamma 0 times square root of n. So this is ensuring that if I take n to infinity with gamma 0 just a fixed constant, like a half or something, or 2, then I'll get a feature learning model.
What is gamma again?
This was just an output multiplier. It was just an output multiplier on the last layer. So I just take literally like these features, I multiply by these weights, and I just downscale the output by this number. So if it's bigger, it's like more feature learning. If it's smaller, it's like a lazier limit. Great. Any other questions at this point? Okay, so we have like an n neuron system, right? So we have these h variables that we want to track, and we want to understand their kernels, right? The problem is there's a n by so you can break this up under gradient flow. There's a contribution from the kind of random initial weights, right, multiplied by my features in the previous layer. Plus, and then you can see it's gamma 0 times some stuff. So all this stuff is from the feature learning updates. But it's sort of hard, right? Because these features are going to change in the feature learning limit. And this is a fixed random matrix. So it's not obvious like how to characterize what's happening in the limit. How do I actually compute, for instance, these kernels and these predictions, these prediction errors? So these equations are exact, but not super useful because they're equations that are holding at finite n for a particular random realization of W0. We'd like to kind of average over W0 and get some kind of statistical description of like what's happening in the limit. So how do you average over these random matrices to compute something about the neural network? So you can use physics tools like a Martin-Séguier-Rose kind of path integral or this DMFT technique, or you can use a kind of like cavity-like method where you imagine adding a new neuron and then computing like the effective marginal statistics of what that new neuron's h variable looks like. In either case, what you get in the infinite limit is a description of the marginal distribution of these h's through time for each neuron in the hidden layer. And basically, all the population averages kind of converge to some limiting thing. So the empirical measure is kind of converging to some limiting measure. So anytime I have an average over neurons or a dot product like a kernel, that's going to turn into some average over some potentially non-Gaussian single site density. So what does that look like? So basically, there's two effects. As n goes to infinity, the kernels that show up in this calculation are going to concentrate. They're going to become non-random and initialization dependent. They're still going to move, but they're going to move in a non-random way. And every neuron is going to be an IID draw from like a single site process. So I had this density on n neurons, and that's going to factorize into a density. It's just a product of the marginals, right? So here's snapshots of training time in like a ReLU network. So here's like h. So this is the value of the pre-activation in this hidden layer. And then basically over time I start Gaussian, but then over time I can get non-Gaussian effects as I train. But the point is, what I'm actually plotting here is a histogram of what the h's are for every neuron in the hidden layer on this data point at this particular point in training time. So this is the kind of thing that shows up. And unfortunately, it's non-Gaussian. So that's going to be unfortunate, and it's going to show up in what comes. But basically, all the things you care about, though, at the end of the day, the macroscopic variables that govern what the network computes are just going to be like correlation functions. So things like these kernels, right, these phi kernels, that just end up being sort of averages over these kind of P of H probability distributions. Yeah.
I mean, this is an ansatz, something that we would like to happen, or you can prove that.
You can prove that this. You can prove that this happens. You can. Yeah. You can show that this happens for random initialization. So you start with a random initialization, and then as n goes to infinity, as the width goes to infinity, this happens. At finite width, it's a bit more complicated. You can compute corrections kind of around infinite width, but this is the infinite width story. It's like all these things converge. Every neuron becomes statistically independent, conditional on these kernels, but the kernels are converging. So that's yeah.
Is it possible to understand to solve the previous dynamics without appealing to statistical physics?
Without appealing to statistical physics. Yeah, so I think there's like there's other derivation styles that use like maybe like iterative Gaussian conditioning kind of arguments. Like if you've seen AMP kind of style things, I think you could use. Those are intimately kind of connected to what DMFT is computing. These like correlation and response functions. But basically, it's like you have to. All these methods deal with this problem of like you have a time-varying signal or a bunch of time-varying signals, but they're propagating through kind of like frozen matrices. And so you have to figure out like what happens when I pass a bunch of time-varying different random variables through basically a fixed frozen matrix. You got to track correlations of these things across time. That's what DMFT is doing. So yeah, so I'm going to write the equation just to show like what it kind of looks like, but we don't have to go into too much detail. But the point is like you can drop the neuron index. You can think about each neuron as just like a draw. It's like a draw from like it's an IID draw from a bucket. It's a random variable now from a distribution, from this marginal distribution. What is the source of noise? Well, there's one source that looks like a Gaussian process. This is kind of like the neural network Gaussian process stuff you might be familiar with. So like at initialization in a neural network, right? These h's are just actually Gaussian random variables. Here, they're Gaussians. There's a Gaussian part to h, but it varies across data and time. Okay, so there's a correlation structure across both. And then there's some complicated, nasty feature learning correction that's non-Gaussian. So this is the hard part. But in principle, you can compute it. And I'll show some plots where we show that this works. But the idea is you can think about this h for different draws of this Gaussian noise. And for different, when I integrate all of this stuff, this gives me some h. Each draw for like a different realization of a draw from the U process is like a different neuron in the network. So it's sort of representing the whole distribution of what the neurons are doing in the layer. And then the order parameters are going to be like averages over this process. So anytime I'm doing a average like one of these kernel computations, I'm basically averaging over these noise sources.
Quick question.
Yeah.
So you're dealing with finite depth right now, right?
Yeah, we could say let's say we're at finite depth. We're gonna.
Do things look simpler as you shape and get deeper?
Okay, so shaping, I would defer to MUFON. I think that's still a little in progress. But if you shape with in a resnet with a 1/√L multiplier, the dynamics look a lot like this, but there's an additional kind of tau index or something, like a layer time kind of index that tells you what fraction of the network you're in. So you have kernels that depend on, instead of a discrete index L for the layer, you have like a function of like data, gradient flow time, and layer time, more or less. We'll have an example of that. Any other questions? Okay.
Is it clear that feature learning correction is doing something useful from this formulation?
Yeah, so you can run this equation. You can simulate these equations on like some of these like sparse polynomial tasks that people look at, like single index models, and this will reduce the error compared to like what the kernel method would compute.
Can you connect somehow this formulation directly to a single index model, or is it?
No. So you pass this thing takes in it's almost like an algorithm. You pass in data to this thing, and it just spits out predictions on test points. So it's like a kernel method or something. Just like how you could simulate the NTK of a randomly initialized network by taking in data and then spitting out test predictions. You could run this algorithm, this complicated integral over training time, and get some predictions.
I understand.
Yeah.
But is there some sort of clear mechanism by which, like for a single index model, for example, something where it's just an observation?
Oh, that was just one example. Like in general, like it's unclear. Like I don't know that there's a general theory of like when you need to learn features or like when feature learning always helps or not. Just for these known examples where people have done a lot of work, like these sparse polynomial tasks, like simulating these, you can see that the first layer weights will like kind of align to the right signal direction in the way that it should, yeah. Like basically like the signal gets amplified in the directions of interest in the right way. But another thing we can do that I'll do right in a second is, okay, well first, yeah, so this whole approach, this whole technique, if you've heard of tensor programs, it's computing the same kind of thing as tensor programs. And it's also, you can recover the PDE-like descriptions on measures for like, at least I've done this, you can do this in two-layer networks because the dynamics for the preactivations are Markovian. So you can map this on to different formalisms that people have looked at for these kind of feature learning descriptions of neural networks. So there was a question like, what does this actually do? Can you compute something? Does this actually match what a neural network does? So unfortunately, like it's hard to scale this to very large data sets and very large training times, which I'll describe why in a minute. But here, this is basically showing a numerical solution to these equations and showing that they match basically what neural networks do. So these are a bunch of 3 hidden layer networks with tangent nonlinearities. And then I can start with a neural network that's in the lazy limit. That's this blue line. And then the dash the dash lines are the theory curves. And then the orange line is I turn on feature learning. So I increase this gamma 0 parameter. And now, like instead of following this curve, the loss kind of goes down a little bit faster. And also the preactivation densities change. But more interesting even is I think that you can see structure in the final kernels emerging, and it's well predicted kind of by the theory. So you can see like the last layer thing is doing this clustering of data points by class. So half the points in the same class are getting high similarity. The points between classes are low similarity. So the initial kernels didn't look like this, but the final kernels do, and it's well predicted by the theory. So that's cool. And then you can also see the time-by-time dynamics. So this is a plot of the t, s components of the kernels. They're also well predicted by the theory. And then you could ask, does this converge? So this is, I simulate the DMFT and I compare running gradient descent with finite networks of width n. And the cosine similarity, this alignment score, so it goes to 1, right, as I make the width sufficiently large. So by width 1,000 or something, this is like a very good description of what's happening.
This is alignment between what and what?
Yeah, so I take all the feature kernels and I just flatten them, and then I do a cosine similarity of the feature kernels for the neural network and for the DMFT. And then the other kernels are these backpropagation kernels, so these G kernels, which are also well predicted by the theory. Okay, and so if this gamma 0 parameter is small, you more or less have the same kind of neural network Gaussian process or NTK kind of story that you had before at infinite width. Things just look Gaussian after training. But if you're in this kind of rich feature learning regime, you can get kind of crazy non-Gaussian effects. But they're still well captured by the theory. And you can also see, like, as I vary this parameter, I'm getting like more and more of this block structure. So I'm doing more and more of this kind of like class clustering, like the supervised information from the labels is entering the network. So that's nice. So are there any cases where you don't have to do like a Monte Carlo procedure to actually solve these equations? So in the previous examples, I was having to like sample from the non-Gaussian density, and that's really hard. It turns out for a deep linear network, if you take the infinite width limit for random initialization, the G's and H's are still Gaussian random variables, so you can still close everything at the level of correlations. So here you don't need any Monte Carlo procedure. The equations kind of close. You can simulate them really easily, and yeah, you can describe like what happens as you vary depth and get good predictions. And if you take like a kind of, I think this is kind of fun. So if you take the kind of infinite limit of this feature learning parameter, it actually matches this infinitesimally small initialization scheme that was studied in this like linear network setting by Andrew Sachs and colleagues. So this connects to the very small initialization dynamics for deep linear networks. So that's kind of nice. Okay, so that was width. Are we ready for depth? Oh, yeah.
Quick question. So I'm wondering what aspects of the dynamics are you tracking, which are you not tracking? So I guess the fact that it's mean field is going to mean that like you've kind of forgotten where your individual neurons are, and that's been forgotten. But like, how about the last layer? What's going on there, and like how? I'm not sure if you talk about the last layer, et cetera. Like, in a high level, what can this predict? What can it not predict that I might be disappointed by?
Ooh, okay, interesting. So I would say this theory right now is not a theory, for instance, of scaling laws. It doesn't tell you why a finite parameter model, when it's trained infinitely long, saturates in performance. So this theory is going to say, I took width to infinity before anything else. Yeah. So it's going to always be in this regime where there's always more neurons than data, always more neurons than training steps. So I think that's the most disappointing part of it. What's the other question? So the other question is, what about the output, the last layer? So that is not so the predictions of the model, like the readouts, the Fs, those become deterministic in the limit. So they sort of, there's some of these like concentrating order parameters, like just like the kernel, those end up being kind of averages that.
So they act on the empirical distribution?
Yeah, exactly. Yeah.
Functional?
Yeah, they're fun, yeah.
Okay.
Great question, yeah, thank you. So now, so now that's sort of the story on width. But if you look at some of these papers, often people are scaling kind of width and depth at the same time, and some of these deep transformer models are getting up in the hundreds of layers, which is sort of interesting. And often these things, like in Sam's talk yesterday, they have these kind of residual structures to them. So there's skip connections across layers that let you like faithfully backpropagate signals. And then usually on the residual block, there's some kind of, depending on the type of model, convolutional blocks or self-attention blocks or MLP blocks. So what would happen, for instance, if we tried taking like depth to infinity in some kind of model? So, and if we did that, could we set up a way of getting hyperparameter transfer across depth? So could we set it up so that if I had a good learning rate in a small depth model, that same learning rate would work in a large depth model? So for general infinite depth limits, I don't know that. I think this is still open. But for resnets, I think there's a couple of different types of limits that we understand. And this was work with these wonderful people, Lorenzo, Mufon, Boris, and Cengiz. 3 out of 4 are here. And what we basically tried, and then actually in the same conference cycle, Greg Yang and colleagues also published a paper on infinite depth resnets with this scaled idea. So you can check that one out for a complementary study. But for our setting, what we're going to do to make things well-behaved at infinite depth is basically alter so we have this skip connection. So we have HL to HL plus 1. But then to make everything stable so that I can have an infinite number of steps, I'm going to downscale the residual branch with the square root of L factor. Okay? And like the claim is, I'm not going to go through everything, but the claim is I can take width and depth to infinity in either order. And if I take them both to infinity, there's some limiting process for all of the kind of important concentrating quantities that I presented in the last thing. So the feature kernels, the predictions of the model, all these things will kind of converge to some well-defined limit. So let's get some intuition for like why this works in a simple calculation. Yeah.
When you say take both to infinity, the order doesn't matter?
Yeah. So this is cool. So if you took width to infinity first, you'll get a DMFT like I described. And then that DMFT is on a discrete set of L layers. And then you can look at the continuum large L limit of that. That gives you a stochastic process that you can characterize. Or you could take depth to infinity first. That'll give you a limiting distribution over all the kernels and neural network predictions and everything. that distribution converges also at infinite n to the same thing. So there's two arguments, two routes to the same limit. In this case, it commutes. But Boris has examples of fully connected networks, not resnets, but in other cases, depth and width don't necessarily commute. So this doesn't always happen. Yeah. But with this resnet thing, with the scaled 1 over root L, it will, yeah. Okay, so let's do like a little intuition pump. So what would happen at initialization? So let's just try thinking about the forward pass through this model. And let's just say let's track what's happening on a single data point. So I just need to basically track the kind of variance of the entries of these vectors h, which I'll denote with this average. So this is a neuron average of h squared. So that's this bracket. So this kernel has a recursion, right? So h in layer L plus 1 is the variance at layer L plus, and then it's the kind of variance of this term, which is beta squared over L, and then a neuron average of this 5h squared, where h is a random variable from the previous layer. So this is a kind of well-defined recursion for HL. So the idea, and this occurred in some of Muffan's earlier papers and some other works, was you can kind of look at this and think, hey, this is sort of a discrete finite difference approximation of maybe some underlying ODE with a step size 1 over capital L. So I could introduce this notion of layer time, which is like the layer index sub little l, script L, divided by the total number of layers. And this is some number between 0 and 1. And I could try looking at like what is, if I'm a fraction, a half, let's say, or tau through the network, what is the kind of limit of h of L times tau? And we can call that h of tau. And then you can just say, okay, well, this thing should converge to a finite difference. This finite difference should converge to some kind of like differential equation. And then the full NTK would be involved not just the forward, but also the backward pass. And it would be an average actually over the layers in this parameterization with this 1 over root L. And this average should turn into an integral over this layer time. And so this is a visualization of that. So like at depth 4, I have like, a kernel like this. And then at depth 8 or 16, whatever, it's getting closer and closer to some limiting thing. And the limiting thing is well-defined and it has a reasonable shape. And this actually won't happen if you do just a standard feed-forward nonlinear network. You'll have a degenerate kernel for like a ReLU activation. But with this shaping or this scaling of the residual branch, things are well-defined. Okay, so what about training? So that was all just initialization. What about training? So again, it's an average over a stochastic process like we talked about for the infinite width case. But now there's this layer time tau. So I have a pre-activation that's a function of layer time tau, data point x, and time t. And it's basically the value at the first sort of hidden layer in the residual stream, plus some integrated Brownian motion. So this is like the Gaussian noise that we saw in the infinite width theory. But now it's a Brownian motion across this layer time as well. And then again, there's a feature learning correction. But now it's an integral over training time, data, and this layer time as well. But it's complicated. It doesn't really matter. But the point is this is the order gamma 0 feature learning effect, right? And the Brownian motion is sort of like local in this layer time, but there's correlations across data and training time. So that's the idea. And if you could sample this effectively and compute averages, you could compute how the kernels are evolving in principle. And then the question is, okay, so how is finite depth different than infinite depth? The finite depth network is just sort of a discrete like Euler approximation of these underlying dynamics. So you have this SDE thing, and then the finite depth network is some like approximation on a grid of that SDE. Okay, and then like, does this do anything useful? So it actually does do some useful things. So for instance, if you just took a bunch of models and tried increasing the depth, and let's say in a small depth model, like this depth 6 model, I tried finding an optimal learning rate. So these are a bunch of models that were trained on like CFAR 10 for some number of epochs. And there's an optimal learning rate right here for this depth 6 model. But if I tried using that same learning rate in like a depth 30 model, the model would diverge. So all these dots that are missing here are like models that didn't even converge. So that doesn't seem very good. It would be nice if like things kind of lined up and I could use the same learning rate. It would be nice if I kind of quickly converge to some well-defined limit. So basically here, the optimal learning rate or hyperparameter is not the same across different depths. But then if you do this scaling that we just talked about, then like you could find the optimal learning rate in the small model, and then it should also be the kind of same optimal learning rate if I increase the width and increase the depth. So there's this well-defined infinite width and depth limit. You can kind of converge to it. You can verify that like all of the updates are order 1 with respect to all the feature updates are order 1 with respect to these numbers. And so there's sort of stable dynamics that let you transfer hyperparameters. So that's nice. OK, we heard about transformers in Sam's talk yesterday, so I won't go too much into this. But yeah, they have this residual structure. You're sort of alternating between MLPs and multi-head self-attention layers. And yeah, there's different ways of making transformers big, right? You can make the number of attention heads big. You can make the number of dimensions per head big. You can change the number of layers, right? So those are the three kind of scaling dimensions we were interested in. So there's a couple of things you can say about some of these limits. So if you want a well-defined stable feature learning limit where you take the inner dimension, the key query dimension to infinity, that's this n to infinity, it will actually, for a randomly initialized network, it'll cause all the attention heads to kind of compute the same thing. So all the attention heads will follow identical dynamics in this n to infinity limit. So if I scale things in a way that's like well-defined and gives me a good limit, that's this purple line. The variance across heads of these attention variables, these keys and query inner products, is actually decaying to 0. So everyone's kind of, all the heads are kind of doing the same computation in this limit, which is potentially bad. And then on the other hand, if you took the number of heads to infinity with this inner dimension fixed, you get a different kind of description. In this case, there's sort of a distribution over attention heads that you need to track. That's the relevant single site density. But that means that there's actually like every attention variable is a random variable. So the attention matrices have a well-defined distribution, but all the heads do a different thing. So that's nice. And you can show that like the finite head models can converge to these infinite head limits at a rate that's reasonable, like a 1 over h kind of rate. So that's nice. And these are just plots showing like consistency of the kind of training dynamics as I go toward this limit, right? So I start at a small number of heads, and I can kind of keep cranking this up to a super large number of heads, and the dynamics are just kind of converging to something, which is nice. And at early time, this should converge roughly like 1 over the number of heads for just central limit theorem kind of reasons. But at long times, you can see it's actually converging at a slightly different rate, right? So the later time dynamics, if I look at the logits for a finite model and compare it to the logits for the infinite model, or proxy for the infinite model, it's actually converging at like some other power law. So this is hints at scaling laws. We're going to try to come back to this in a minute. Last thing is depth scaling in the transformer. So I told you about the square root of depth thing. There's actually, you could imagine different choices. So anything with this exponent between 1/2 and 1 gives you a well-defined limit where the residual variables update by order 1. So you get feature learning in all of these limits. But the nature of the feature learning is different for models that have multiple layers per residual block. So if I have a model like a multi-head self-attention model, where there's sort of key matrices, query matrices, and value matrices, if I use 1 over square root of L, which is the depth scaling I was talking about earlier, the key and query weight matrices are actually freezing. So the amount they change over the course of training is actually decaying to 0 as I increase depth. But if I choose instead alpha equals 1, which is this other extreme that's allowable, it actually maintains consistent feature learning. And in this limit, this other limit, which we now think may be better for transformers just because it lets every layer learn, in this limit, all that Brownian motion that we had in the SDE case kind of disappears, and you instead have like more of a neural ODE for your training dynamics in the forward pass. And in practice, yeah.
What kind of optimizer are we modeling?
So either Atom or SGD. Yeah, you can do either.
Wouldn't the answer come out very different just because the update scales of Atom are very different to the update scales of SGD?
No, so there's different choices for how to choose learning rates in these two optimizers, but this conclusion is the same. So if I adopt the 1 over square root of L thing and I use Atom, for example, I still suffer from this problem. If I do Atom with 1 over L, I can escape the problem. Same with SGD. Yeah.
Can you give some intuition for why the key and query matrices are forbidden from moving?
Yeah. So it's a bit subtle. Okay, so I can describe basically what's causing this is. So I have like a 1. Let's say I had a 1 over L to the alpha thing here, right? I want basically after the output of each layer, I want it to give me a contribution to the residual stream that's from feature learning that's order 1 over L. So that sets basically how fast the weights in these models, in these layers can move. If they move faster than that, then it actually causes me to accumulate too much of an update on the forward pass from feature learning. So it's a stability kind of thing. And if I choose the learning rate that's right for 1 over L, it kills the initialization noise, like it kills the Brownian motion, but it lets me have order 1 updates in every hidden layer and also in the last layer of the residual block. Does that make sense?
Wouldn't that argument apply to the previous resonant case as well?
So no, because you have to, so if this was 1 over square root of L, then to get a well-defined thing, the weights in this hidden layer, or in these layers have to move by 1 over square root of L. If they moved faster than that, then the total update would be too large. Yep.
When you were asked about Atom or this optimizer, I mean, what aspects of the optimizer are you modeling here? I'm just kind of curious.
Right.
That.
Yeah. That's a good question. So for Atom, the rough heuristic is like basically modeling it as sine GD. So you can think about it basically like it's the learning rate times an order 1 number. That's the size of the weight update. So you need to choose the learning rate so that that kind of update gives you like something well-defined with respect to width and depth. And the reason that you model it that way is because Atom is sort of dividing by the square root of the running arm. It's like the RMS norm of like the gradients up to some time. So it's roughly normalizing the gradients. But yeah, you could say like we can exactly say what you should do for sine GD or for SGD. And then sine GD is our like proxy for Atom.
So why did you then, at the very beginning of your talk, had NTK, why the behavior depended on this gamma parameter? Or was this true only for stochastic gradient descent, or was it also true for Atom?
It's also true for Atom. So you can linearize any model by doing this thing. So this gamma trick can let you like linearize a model if you make it small. The way to see that is like if gamma is small, then the amount that the parameters need to move to accomplish an order 1 change in the output is also small. So regardless of the optimizer, you can converge to a linear model. It's a different kind of kernel that governs the dynamics, but you can converge to a linear model for any optimizer by doing this rescaling. Does that make sense? Okay. Yeah, but I'm happy to chat more about like why this is. So I was actually chatting with Mufon about this the other day, but we were like, maybe there's a way to get around this, but I actually am convinced that there's not a way to get around this. So you have to choose between, do I want noise at initialization on the forward pass, or do I want feature learning in every hidden layer? It's sort of a forced choice.
Can you compare this prescription like to avoid the decaying of or the kind of potential determinism of these two things with standard practice, and whether you see people in practice somehow tending to parameterizations or scaling that would have feature learning continue in key and value?
Yeah, it's a great question. Maybe Sam's a better person to ask than me, how people are scaling up depth in practice. But yeah, I mean, right now we're not exactly sure what's the most realistic thing. I mean, in some sense, it's yeah, I don't know.
So people do a range of things between square root L and L.
Okay.
But normally the square root L is like an accidental consequence of normalization rather than an explicit factor.
Okay.
And then like often the other factors are more like they're like imposed within it. They're not like hard-coded factors. It's more like adding it, like scaled down this layer by some factor. So it's like similar but not exactly the same.
I see.
Is the general argument for the alpha L equal to 1 thing being like, okay, well, however much you change, when you divide it by L to the alpha, you want this to be order 1 over L.
Yeah.
So like if alpha is anything less than 1, then the change you'll desire is smaller than order 1, which means your dynamics will be lazy, whatever the block is.
Yeah, exactly. Yeah. Exactly right. And then, yeah, this is just a table, and like Sam, again, probably Sam would know better, but I was just looking like, what do people actually, how are people increasing the size of their transformers in practice? So if you just look at like the GPT-3 paper, it seems like everything's kind of being scaled up at the same, so they're increasing kind of like number of layers, they're increasing the number of heads, and then maybe it's a doubling of the dimension per head, but it's not a crazy change here. So it does seem like, taking heads and layers to infinity is like, a good idea, and then the Llama paper, it's a similar thing. They're increasing heads and layers. So I think I also don't understand quite what's the best architectural trade-off, like what sets the optimal like aspect ratio or something between like depth and width. This is not super well understood. Because this involves basically like, right now I've just told you about limits, right? I didn't tell you about like what's the cost of having a finite size model, which is what you'd need to understand scaling laws. So there's a practical issue, right? In practice, like as a theory, right? Like what is the problem with this theory? The theory is actually really hard to calculate. So if I just wanted to compute a kernel method, and I have p data points, it's like a p cubed cost, right? I got to invert a matrix. If I want to solve the equations that I presented today, it's sort of, if I do t steps of training, it's p cubed, t cubed kind of time complexity to solve these equations, right? That's really bad. Training a neural network is linear in the number of steps, linear in the data. So okay, so that's good. I mean, yeah, I pay a cost in terms of parameters, but it's sort of like once I train, I don't have to like revisit any data points to figure out what's happening on a test point. So I benefit dramatically from having the neural network. So solving our thing is only faster if you care about super, super wide networks, like networks of the order width is bigger than samples times time, which is not the relevant regime, unfortunately. In progress, we're sort of working on like non-parametric Markovian approximations to these dynamics. So you can try writing down recursions that are very close as possible, I guess, to the dynamics you would have in a deep network. But that maintain a Markovian structure so that you can reduce the t cubed time complexity down to order t. So this is a little bit closer to what you have for the kernel method. It's still a lot though. But okay, so these are all like practical issues with just like, can you compute stuff with this? Is it better than training neural networks? But there's a theoretical issue. This gave us a picture of what's happening at infinite width. What problem is, are there theoretical problems with this picture? I took width to infinity first. I kept sample size fixed. I kept training time fixed. Is that a problem? So another way to say that is, what do finite size effects do in this parameterization? Like, why are finite networks different than infinite networks? Or what sets scaling laws, right? That's the question. So there's two things you can do. You can just do a bunch of sweeps. You can do like a bunch of experiments and very in this parameterization, look at like how fast you kind of converge to the limits. And then the other thing you could look at is sort of toy model, right, of neural scaling laws that I'm going to discuss. The first thing is basically, I realize maybe I'm running out of time, but I'll quickly kind of go through this. Basically, this is work with Nikhil, Alex, Depin, Saab, and Genghis. And we basically tried like asking when are models really close to their limits. So this is a bunch of resnets on CFAR 5M. So it's like an extended version of CFAR trained with like a generative model, so you can stay online. And these are just different width models. And you can see the width, even the width 32 model is very close to like the width 512 model. I imagine if you kept going, things would still look very similar, right? You're basically there. You basically have converged to the limit, so that's nice. If you have a harder task like ImageNet, right? Obviously, as you keep training, you have to go wider and wider to sort of see convergence to the limit. And then if you do like language modeling or something in a transformer, you also have to kind of, like things are close early on, but as you keep training, the finite size effects kind of compound and build. So at some point, you are doing you're doing much worse in the finite model compared to the infinite model. But early in training, they're pretty close. When this works, their kind of mean field idea is very, very, very good. Like the pre-activation densities across different widths are actually like basically the same. So this is the CFAR example. And the feature kernels are also basically the same across different widths. So there is like a lot of consistent representations being learned, basically across different model sizes, which is nice. Okay, so that was all about, these were a bunch of, that was all empirics on like how fast you approach this. In practice, people see that the scaling laws usually look like, if I train for t steps in a model of size n, it's some error that scales as a power law in steps and a power law in n with some alpha and betas that they empirically measure. So here's just a simple example on like a vision task. And here are some examples from the paper I was just mentioning. So these numbers are like specific on like the type of task and architecture that you're looking at. So if you do something on ImageNet or on like Wikitext in a different kind of model or different architecture, you'll get slightly different exponents, right? So what sets these exponents? Is there a toy model that tells you about these? So so if I train a long time and long enough for the kind of models to have diverged in performance, what sets their scaling law exponent? And then what sets the kind of trade-off between, like if I wanted to be compute optimal, if I wanted to figure out like how should you give me a compute budget, what is the best way to scale up model size and training time so I get the best possible error? So what sets that? So we had a toy model recently that we worked on with Alex and Jengis. Given the time constraints, and maybe I'll jump through it. But basically, first we're going to think about basically a random feature model. So first we're going to turn off feature learning, and we're going to think about a model where there's basically the student has access to features that are projected through some kind of random initial projection. So through these coefficients A, and that gives me a finite width kernel within features, right, or in parameters. We know that if I randomly initialize a neural network, right, I get a kind of slightly different kernel every time from the random weights. So this A needs to be a random matrix, and it also needs to have the property that the finite width kernel needs to approach the infinite width kernel as the number of parameters goes to infinity. So there's many A's that do this, but we just are going to think about the simplest possible A, which is just a completely isotropic random A matrix. And so you can expand basically you can have a target function that you can expand in this basis of, let's say, like infinite width kernel eigenfunctions. And you have a student function that you also expand in this basis in terms of the A projection and the trainable parameter W. So it's just a random feature model. But the point is, you can have finite data, so you can have P data points, and you have in parameters. And if you just write down what does gradient flow look like on this model, so the error variables, which are these V0s, so this is how close is my optimal weight to the effective weight of my student, so the teacher to the student. This thing evolves as a kind of linear dynamical system with a product of these two matrices. So this is a kind of interesting random non-Hermitian matrix. If I have a random sampling of the data with P data points and a random sampling of these projection coefficients within projections. So the test loss I get by just looking at a certain norm of this V0 vector. And so this is equivalent to looking at basically the dynamics on a structured random feature model. So the statics of this have been studied and works even by people in this room and several others. But what we want to look at is this compute optimality where you can train for a certain number of steps or vary the model size. So that's something we're interested in. And the key insight that you can see just from this equation, before we do any kind of random matrix theory or any averaging or anything, you can just see that if these things are finite rank, there could be a null space in this matrix. And if there's a null space, there are directions where basically I won't make much progress. So basically, in those directions, I'm not going to learn anything, and I'm only going to capture a fraction basically of the real signal W star. So that's going to limit generalization. So if n goes to infinity, this becomes a full rank matrix. If p goes to infinity, this becomes a full rank matrix. And if I train long enough, I'll be able to converge. But otherwise, I could get stuck at long time with some final error. So it's a game of calculating how loss depends on training time, how loss depends on model size, and how loss depends on data. Okay, and the last thing is, empirically, if you just diagonalize kernels on real data sets, they often have these kind of power law eigenspectra. Right, so this is an MLP with data on the circle, just different nonlinearities. And then this is CFAR5 images in a CNN. So you often, if on a log-log plot, right, you see these lines, like we've heard in previous talks. So so what happens? So you basically have two settings. You have a setting where you're bottlenecked by the amount of training time that you've had. So the loss is very close to the limiting loss if I had infinite parameters. Or if I train long enough, I eventually saturate and I hit something that's dependent on model size. So this is captured by the model. Or if I have limited data and I keep training on that same data, I can eventually become limited. So this sort of relates to maybe some stuff Elvis was talking about, right? So if the total amount of data is just getting repeated and I'm not making any progress, then even if I keep training and putting more compute into it, I can get stuck. So the key idea is the loss sort of has these three regimes. You can be bottlenecked by training time with a certain exponent that's computable in terms of spectra that you can measure from the data. You can be bottlenecked by model size, or you can be bottlenecked by the total amount of data. And the intuition is basically if I ran this gradient descent in this setting, it's capturing some number of spectral components of the target function. It's sort of the minimum of something that depends on time, something that depends on n, and something that depends on p. So that's like a rough heuristic that gets you the right scaling laws. And you can make these kind of compute optimal plots. So if you plot things for different model sizes as a function of training time, you can back out of this argument, you can back out a compute optimal scaling law. So if I chose model size and training time optimally to stay on this Pareto frontier, what is the scaling law with respect to compute. So that's sort of nice. And basically, depending on the geometry of your data, depending on how fast the kernel eigenvalues decay, you get a different optimal policy for how to scale training time and model size. Okay, okay, it sounds great, right? Nice theory, but it doesn't actually describe, so it's descriptive of networks when you explicitly linearize them. So what I just told you about was a random feature model. It's sort of descriptive of like neural networks when they're trained in this lazy regime. But if you let networks learn features, they're on a completely different kind of compute frontier. They're much more efficient. They train much faster. So what's going on? So I got this blue line by diagonalizing the kernels at initialization, and then just plugging in like what would happen in a linear model. And these are all linear models, these solid lines. But the dashed lines are models where I let the model do feature learning.
What's the architecture?
This is CNN on
Great.
CFAR. Okay, so in this newer thing, we were like, what's the dumbest model of feature learning? So in the previous model, we basically had some base features, an infinite number of base features. We had a random fixed projection. And then we trained some weights here. What if you just added a layer where you let this internal layer train? So I'm allowing my features to mix, or I'm amplifying maybe important features. But then I still train a readout to sort of train my prediction. So this is the simplest kind of toy model you could hope for. Maybe it'll capture something, maybe not. But what's kind of cool is it predicts that, it makes a strong prediction for power law features. So for power law features, if the task is easy, so there's some number beta that's related to the difficulty of the task, so how fast the target weights decay. So if beta is bigger than 1, the task is in the RKHS of the initial kernel. So the task is sort of easy or solvable quickly. So here, even if I turn on feature learning, it doesn't do anything. It doesn't change the scaling law. It just sort of accelerates by a constant factor the loss. But if I look at hard tasks, so tasks where the RKHS norm is actually infinite, in this case, turning on feature learning actually gives me a different scaling behavior at long time. So the blue line is the lazy model, and then the rich models are like actually on this different scaling curve. And the exponent is roughly double. This is the new exponent that this toy model predicts as a function of the old exponent. So you see if you're lazy, you're on this blue line, just they're equal. But if you're in the rich regime, you get an acceleration for like hard tasks. So that's sort of nice. Does this actually work on real stuff? So that was all a toy model. What's crazy is you can take nonlinear networks, so like nonlinear NMLPs. Okay, so this is a depth 4 ReLU MLP. Train it on, so I'm training it on a bunch of sinusoids. Why am I doing this? So if I just randomly initialize data on this circle, these are the eigenfunctions of the kernel. So I can choose basically how fast the target coefficients decay. So here I have complete control on how hard the task is by manipulating these exponents q here. So I can basically choose these q's that set the rate of decay of the eigenspectra of the task. And what's cool is the new exponent is actually quite predictive of the scaling behavior that you get. So there's some dashed red lines, maybe they're hard to see, but there are dashed red lines that are actually predicting kind of the scaling laws you're getting when you train networks in this, on these tasks, which is sort of cool. And so if you do like MNIST digit recognition, so if you linearize the model, so if you make gamma super small, it's well described by the t to the minus beta. So you do the spectral diagonalization of the initial kernel, you get this number beta, that's the blue line. But then if you allow the network to learn features, so you crank up this gamma parameter, it's on this other scaling behavior. It has this different scaling law that's sort of well predicted by our toy model, which is sort of fun. And then, okay, there's a failure case. So we were initially motivated by CFAR 5M because we noticed this blue line does not describe what's happening in the rich regime. For a time, it looks like our thing is matching a little bit, but then something else happens, and we don't really understand this regime. So I'd say this is like maybe a partial toy model where you can see some acceleration due to feature learning that changes the compute optimal scaling. Yeah. So that's the main story. I'd like to just thank all my wonderful collaborators, including some of the people here. It's been great catching up, and also just sources of funding. Yeah, happy to take any questions.